Hello, hello, hello. In this worked example, we're going to discuss the concept of displacement. And what do we mean by displacement? Well, let's suppose you have some initial position, which is indicated by a vector Ri. Ri is your initial position. And then you move to some final position, and we'll call the final position vector R sub f. Then by definition, the displacement vector is your change in position. So delta r is the displacement. And we can see from this picture that r sub I plus delta r is equal to r sub f. Okay, so let's test out our understanding of the concept of displacement by taking a specific example. So this example involves three different cities: Toronto, Detroit, and Washington. And we're told that Toronto is 320 kilometers from Detroit in a direction 26 degrees north of east. Washington is 625 kilometers from Detroit in a direction 39 degrees south of east. And we want to know that if you take a trip from Washington to Detroit to Toronto, what is your displacement? So what we want to do here is to draw a picture to translate these words into some visual representation. So let's do that. So I'm going to start by drawing a set of coordinate axes, and it's natural to represent our to orient our coordinate axes so that the x direction corresponds to east, and the positive y direction corresponds to north, and west is over here, and south is over here. And now on this coordinate axis, I want to draw where my cities are. And since in the story, uh, the city's positions are being measured relative to Detroit, it's natural to place Detroit at the origin of our coordinate system. So I'm going to put a little red dot at the origin, and I'm going to label that with a D to stand for Detroit. And now we're told that Toronto is 320 kilometers from Detroit in a direction 26 degrees north of east. So I'm going to draw a line. I'm going to make it approximately 26 degrees north of east. And at the end of the line, I am going to put a dot, and that dot is going to represent the city of of Toronto. And I'm going to put a little arrow on my line to indicate that this is a vector quantity. And I'm going to call this vector R sub t. That's the position of Toronto in this coordinate system in which we've placed Detroit at the origin. Similarly, I'm going to draw a line from Detroit towards the direction of Washington, and we're told that Washington is 625 kilometers from Detroit. So I'm going to make this line a little bit longer, and the direction is 39 degrees south of east. So I'm going to try to make that look like something like 39 degrees here. So the um, the end of this arrow represents the city of Washington. And now let me label my angles here. We said that Toronto was 26 degrees north of east. So that angle here is 26 degrees. And Washington is 39 degrees south of east. So that's a 39-degree angle. And this vector here, which represents the position of Washington, I'm going to label R sub W. And now we want to know if we take a trip from Washington to Toronto, what is our displacement? So I'm going to draw a line from Washington to Toronto. I'm going to put an arrow on the tip here. And this line represents my displacement. That's the change in position in going from Washington to Toronto. And we see from our picture here that if I start in Washington and add my displacement vector delta r, I'm going to end up in Toronto. And now what we want to know in this problem is what is our displacement delta r. So all I've got to do is to rearrange this equation. I can solve for delta r. I'm just going to subtract r sub w from both sides, and I get my displacement delta r is just r sub t minus r sub w. Okay, so this represents an expression for the displacement, but we're really not done yet. I'd like to give a numerical answer for what the displacement vector is. So how are we going to do that? So if I really want to come up with a numerical answer, I have to subtract two vectors. And the best strategy for coming up with numerical answers when you're adding or subtracting vectors is to represent each of the vectors in sort of Cartesian coordinates, or in other words, in terms of unit vectors I hat and j hat. And then once you've done that, adding or subtracting vectors is pretty easy. So let's see how that works. So what I'd like to do is to find expressions for both RT and RW in terms of unit vectors I hat and j hat. So to do that, I'm going to just redraw the set of coordinate axes here. And for now, let's just focus on RT, the position vector of Toronto. And I want to find the x and y components of that vector. So to find the x and y components of RT, I really want to find the lengths of the two sides of the two perpendicular sides of this purple right triangle here. And in order to find these lengths here, we have to remember that we were told that Toronto lies a distance 320 kilometers from the origin of our coordinate system, which you recall was the city of Detroit. So in this right triangle here, we know the length of the hypotenuse, and we know an angle here, so it's quite straightforward to find the lengths of the other two sides. The length of the horizontal leg of the triangle is just going to be 320 kilometers times the cosine of 26 degrees. And the length of the vertical side of this right triangle is going to be 320 kilometers times the sine of 26 degrees. And plugging into my trusty calculator, I find that the vertical leg has a length of 140 kilometers, and the horizontal leg has a length of 287 kilometers. Well, actually closer to 288. So what that means is I can express the position vector of Toronto as 288 kilometers times I hat plus 140 kilometers times j hat. Okay, and now I want to do a similar thing with finding the coordinates of my r sub w vector, the vector which gives me the position of Washington. So here is r sub w. Here's my Detroit is at the origin, and we're told in the problem that this distance here is 625 kilometers, and that the angle here is 39 degrees south of east. And what we'd like to do is to find the x and y components of this vector. So now The triangle that we want to focus on is one that looks like that. And so we want to find these two lengths. And this top length here we see is the x component of the vector r sub w is going to be 625 kilometers times the cosine of 39 degrees. And this length here is going to be 600, the vertical length of this triangle is going to be 625 kilometers times the sine of 39 degrees. And again, plugging into my trusty calculator, I find that this vertical length here is 393 kilometers. And this horizontal length is equal to 487 kilometers. And so now when I want to write down my numerical value of the position vector for Washington, it's got a x component, a horizontal component of 487 kilometers times I hat. And now we got to be careful in the y direction. The y component is negative. That is, the r sub w points in the lower quadrant here. So it's going to have a negative y component. So I'm going to write this as minus 393 kilometers times j hat. And so now to finish up, all I've got to do is plug these numerical values into my expression for the displacement delta r. And let's do that right up here in the upper right-hand corner where there's space. So delta r is equal to, I'm going to plug in for r sub t is 288 kilometers I hat plus 140 kilometers j hat. And now I've got to subtract from that r sub w. So I'm subtracting 487 kilometers times I hat minus 393 kilometers times j hat. And what does that equal to? Well, all I've got to do is numerically subtract the x and the y components. So 288 minus 487, negative 201 kilometers I hat. And now when I'm subtracting a negative number here, so I've got to add 393 to 140, and I get my y component is going to be plus 533 kilometers times a j hat. So that is my answer. This is the displacement vector. If you travel from Washington to Toronto, you have a displacement. It's a negative displacement in the x direction and a positive displacement in the y direction, and that is your displacement vector. So that's it for this worked example. Hope to see you again soon. Bye-bye.